Okay, so let's move with the first talk of today. So scanning probe microscopy at the quantum limit, which is of course a very ambitious title. So for less than 20 minutes, so we have the clock over there. But my goal is mostly to bring some motivation and prepare the ground for the upcoming talk and discussion for the rest of the day. So let me start with the people slide first, because at Zurich Instrument, we believe that people makes a difference. So we like to engage with our customer on a deep technical level. And so that's why we have a nice team of application scientists with a physics degree and different application background. So in photonics, sensing, scanning probe, quantum technology, of course, with many different cubic flavor. And we have found that, from just a pure distributor and reseller point of view, it's difficult to have this level of interaction. So that's why we like to be as close as possible to our audience. And I hope that user meeting like today it's a good indication of that. But Zurich Instrument is also part of Rohde & Schwarz since 2021. So of course, Rohde & Schwarz, it's a much bigger company. So we are part of the test and measurement division. So I'm sure that you already know some of the RF line, which is very well recognized in the field, especially DNA network analyzer, oscilloscope, fast spectrum analyzer. And actually in the past, we had been working with RF synthesizer in many different labs. So the synergy was quite obvious. And coming from Zurich Instrument, we have a bit more of an academic understanding and qubit control and all that. But so clearly there will be more synergy coming up from this. And I think it's good that you're aware of that. Yeah. But okay, now this brings me to the outline of this talk. So I will have just 3 parts. So the first one, as I said, it's mostly about motivation. So SPM, which is a very nice nanoscale imaging tool. So how can we bring that to a kind of a quantum age? And that means so typically adding a coherence. And to some extent, I think we owe a lot to the pioneering work of magnetic resonance force microscopy already quite some time ago. So it's some continuation on that too. Then the second part will be on our new instrumentation, because that will be related to the tutorials that you will see. And of course, the last part, which will be, as I said, preparing the ground for the upcoming talks. So, and here I just added this nice nanosquid on a tip from just as an illustration. So you can have squid on tip, you can have squid on cantilever, you have this superconductor, Josephson junction in a loop, so you can be sensitive to the magnetic flux, but NV center can also be to the magnetic field. Yeah. Okay, so microscopy is mostly about imaging. And especially for scanning probes, that means that you are doing a lot of tip sample interaction. And so SPM is really about, creating contrast out of this information. And we do not actually have AFM. So we like to collaborate with our customer and partner. So here I'm actually taking some slides from a previous user meeting, and I'm sure you're going to have very nice pictures in this one as well. So yeah, SPM then is so here we have, for instance, Kelvin probe, piezo response, nanomechanics, thermal, and so on. Yeah. So we are, of course, as I said, grateful to the collaboration with all these people, and we look forward to more. But, AFM has quite a complex zoology with many abbreviations. And so let me guide you through some of that. So we are not an AFM manufacturer. So that means that we more like an enabling technology. So allowing you to have basically some sophisticated toolbox from which you can draw so of course, some nice PLL, some lock-in and so on, some imaging capability. And so from that, you can do, let's say, some first single frequency mode. So that will typically give you a single channel of information. But you can also go to multi-frequency. So that means like starting to add, mixing different modulation scheme. And so for this, we can extend this toolbox further. So obviously with some multi-frequency capabilities, some more complicated PID patterns, some heterodyne schemes, sideband analysis, and so on. Actually, the parametric sweep is very important to explore your parameter space, and also to understand some open loop and closed loop transfer function and so on. So with this, you can, of course, then enable additional mode, such as Kelvin probe, where we had some previous webinar, and so on. And now there is actually the possibility to go even beyond this, so actually to the microwave regime, so where you have have a different type of interaction, but you can also start to have some better time resolution. And that requires some additional tools, especially with higher data through rate, RS sweep, this microwave locking that you will see today, and of course some arbitrary waveform generator, because that's really the type of tool that enables to do a POM probe. And in our case, most of the time, electrical POM probe, so better time resolve experiment. So that's just to give you an idea. But okay, all this, so some of this will actually be discussed, in depth, or at least in some of the talks that you will see today, and from this different area. But all these SPM modes did not happen overnight. And we tend to think about technological progress as a linear thing, but I see it more as something rather non-linear and actually more like building on, tides or waves. And so you start with typically a slow progress, and you have a very high growth spur, and then you have some maturity phase. And often the previous technology is leading to the next wave. And, SPM is actually already 40 years old. And, we could identify maybe some big trend. Obviously today, especially in physics, quantum technology is it's a very hot topic. But 20 years ago, when I was doing my PhD, nanotechnology was also a very hot topic. And of course, you can trace back to what you want. So computer technology, you may think, okay, it's a bit out of scope. But by this, I also mean understanding and mastering semiconductor physics, to some extent superconducting as well. And so that explains a lot of these different modes. And I'd like to emphasize, so for instance, one of the very first SPM manufacturer back in the 80s was called Digital Instrument. They did not call microscopy or AFM or anything. So digital was already something very important back in the day. And the first FPGA was also done there. Which actually at the time was a very niche, but nowadays any modern control electronics has FPGA inside. And when you think about it, the first STM image, you had not even a full image, you just have some line scan, which was acquired in an analog fashion. But when you see all the wealth of AFM mode that came later on, it would have been very difficult without some sophisticated control electronics and so on. But of course, then you have nanotechnology, and these you are also very familiar. So that's moving from the bulk to 2D to 1D to 0D. So graphene, carbon nanotube, nanowires, quantum dots, whether they are self-assembled or lithographically defined. So these came all out of this. And now, of course, we are in this quantum technology thrust. And if you want to put some milestone to these different waves, I think atomic resolution was definitely one of them. And now it's kind of routine, but when you think about it, for a long time, physicists did not believe that you could actually see atoms. We believe we could know what an atom is, but make an image in real space, that was quite a feat. And maybe 10 or 20 years later, we were able in a single quantum dot to detect a single electron, which was also quite a feat. And now, which I actually would not even have believed, we can even control single spin. So, and maybe as a wrap up of this section, I like to pull this science paper literature. So basically from Andreas Heinrich, that was both in IBM and now in Seoul, where you have actually this old 1981 apparatus STM, which is normally you just have DC, and which is able actually to look at an atom if you want. But then if you add some fancy electronics, like RF generator from Roder and Schwarz, some nice AWG and lock-in from Zurich Instrument, then not only can you image it, but you can control a single spin of a single electron in a single atom. And so here you then benefit even from this type of resonance enhancement about this electron spin resonance. So here, of course, electron is at 20 gigahertz, but yeah, which is still a little bit further what Zurich Instrument lock-in can do nowadays. But yeah, with Roder and Schwarz RFs, you can also do that. Yeah. Okay, so that brings me to the new instrumentation and some motivation for the upcoming tutorials. So yeah, so we came with actually now even two, which you actually see here very nicely, kind of new generation of lock-in addressable up to the gigahertz. So the SHF Li is actually, so Li is for lock-in. Huh? So always keep this in mind. SHF is just super high frequency. It's coming from our SHF family, which are also extended for quantum computing analyzer. And the GHF Li, so for the direct RF digitization. And that really brings what we are very familiar, you know, about high noise rejection and so on to the gigahertz regime. So that for the lock-in part, and that will be addressed in this morning tutorials by Kivench. And then you will have, when timing matters, and you also want to control, yeah, so you want to have better coherent control about your waveform, controlling delays, phase, and so on. Then you will use the signal generator, and that will be addressed with Emilio. But because this will not be discussed directly in the tutorials, let me just have a small also motivation slide. So why did we even bother doing this super heterodyne scheme, which in principle, it's a lot of hassle? Because you may think, okay, brute force digitization, that's the way to go. It's easy, you have no data loss. But the reality is that it doesn't come for free. So, you know, it's not only is it expensive, but usually you have lower vertical resolution. You have massive amount of data. And the truth is that you don't care about the carrier. What you care is about the IQ product. And so you need to downsample it anyway. And so for this, you need to have good processing power, and you don't want to use this processing power for, you know, just oversampling. The other thing is you could just do IQ mixing, which can also look like the smart data approach. And then you can mix with any RF source you want. But okay, this also comes at a cost. Like eventually it requires more complicated mixer calibration. You are more sensitive to drift and so on. And in the end, the analysis bandwidth is actually not so high. So that's why we did bother with this super heterodyne, which is actually not new, but it is implemented in a new way and available now for everyone. And the truth is that you don't have to care how complicated it is, because it's just at the end of the day a white box which will actually do what you want. And then this allows you to actually demodulate faster with no mixer calibration. And we think it's actually benefiting from both worlds. Okay. So again, I encourage you to attend the morning and the afternoon tutorials, because that will be more concrete and also showing basically the user interface of lock-in with Lab 1 and of quantum generator with Lab 1Q. Okay, so the last part. So I think I'm even on time, so this is great. Which actually it's only last two slides. So this will, of course, be discussed at length from an application point of view from our nice speakers today. But here I wanted to illustrate how we typically connect, in this example of the NV Center, some of our instruments. So you don't have to, so here you can use, your local oscillator, for instance. So typically from Roder and Schwarz, you have IQ mixer. Then here you have actually pairs. So for both I and Q, you can have it 2 times. So if you want to have multiple tone, that is then driving the microwave for manipulating the spin. So of course, the spin, it's a small splitting of a few gigahertz, but then you also need to pump it with lasers. And so for this, you are using some nice digital lines that you can trigger a bunch of lasers with this. And one nice feature of the HD AWG is that it also include a counter option. So you can also do some of the optical detection from the photo counter. And if you don't want to bother with this rather complex, electronics around here, then you can just upgrade to the SHF Signal Generator. And so with this, you have actually a single output here that you can directly connect to the microwave antenna. You can have multiple tones if you want. And that simplifies it a lot, and use an external card. Okay, so let me jump to the conclusion with a rather bold statement. So quantum needs SPM. I think that really helps to better test and understand quantum material property at the nanoscale. And that also helps to understand some decoherence effect due to substrate environment, some defect, when you have a problem at the gate, And something, so SPM, it's not only an imaging technique, but it can also manipulate single atom, of course, but it can detect single electron and even address single spin. And that was main message I wanted to pass here. So now the floor is open to our great speaker for today. So we will have 3 talks in the morning, 3 talks in the afternoon,